Earth is the blue planet. It is blue because of the large amounts of water found on the surface. 70% of the Earth's surface is covered in water, and while over 95% of the water on the planet is found in its oceans, there are also large amounts frozen at the planet's poles, as well as smaller but important quantities underground, in surface reservoirs, and in the atmosphere. The ubiquity of water across the globe and in our daily lives makes it easy to take its importance for granted, but its central role in supporting life and in the movement of energy on a global scale stems from its chemical behavior, which is due to the unique chemical structure of water molecules. A molecule of water is one oxygen atom covalently bound to two hydrogen atoms. Its chemical formula is H2O. The arrangement of the p orbitals of the central oxygen atom give water its asymmetrical shape. Oxygen is more electronegative than hydrogen, so the bonds are polar covalent bonds. The combination of the polar bonds and the orientation of the bonds makes water a polar molecule, with positive dipoles near the hydrogens and a negative dipole near the oxygen. Positive dipoles of water molecules are attracted to the negative dipoles of other water molecules. This attraction allows water to form hydrogen bonds. Each water molecule is able to form hydrogen bonds with as many as 4 other molecules, so while each individual hydrogen bond is weak, the combined strength of the many hydrogen bonds formed between multiple water molecules creates a strong attractive force that holds water together. This attraction between individual water molecules is what gives water its strong surface tension, which allows things like this paperclip to float even though the metal in the paperclip is much denser than water. Surface tension is caused by the attraction of water molecules to each other due to hydrogen bonding. This strong attraction between water molecules is also why water has such a high melting point, a high boiling point, high specific heat, and high latent heats of melting and vaporization. Consider a similar molecule, H2S, or hydrogen sulfide. Since sulfur is in the same column of the periodic table as oxygen, it needs 2 electrons to fill its outer valence shell, giving H2S a structure similar to that of water. But sulfur is not as electronegative as oxygen, so the covalent bonds in hydrogen sulfide are not as polar as they are in water. As a result, hydrogen sulfide does not have strong dipoles, meaning it does not have the capacity to form hydrogen bonds. The lack of hydrogen bonding makes this a great comparison to demonstrate how hydrogen bonding influences the chemical properties of water. Hydrogen sulfide has a melting point of negative 85.5 degrees C, a boiling point of negative 60.7 degrees C, and a fairly typical specific heat of 0.23 calories per gram degree C. Contrast this with water, which has strong dipoles and the ability to form hydrogen bonds, resulting in much higher melting and boiling points, as well as an unusually high specific heat. Water is called the universal solvent, and like these other properties, it is water's polar nature and its ability to form hydrogen bonds that make it such a good solvent. Water is particularly good at dissolving ionic bonds. Take common table salt, which is a solid made up of sodium and chloride ions connected by ionic bonds. Water can dissolve salt because as a polar molecule, individual water molecules can orient in such a way as to isolate individual ions in an ionic solid, allowing the dipoles of these water molecules to disrupt the ionic bonds, pulling the ions apart, while water's dipoles compensate for the charge of the ions. In contrast to the ease with which water dissolves most polar and ionic compounds, neutral and nonpolar compounds such as fats and oils are not readily soluble in water. The polarity of water also plays a role in water's unusual density profile. In most materials, density increases with decreasing temperature. As temperature drops, a compound becomes more dense. Then, at the temperature at which it undergoes a phase change, say from liquid to solid, there is an abrupt increase in the density as the molecules become locked in the rigid formation characteristic of a solid, which then maintains a fairly constant density as temperature continues to fall. Water behaves similarly as a liquid, with increasing density as temperature falls, but as it approaches its freezing point, the rate of change decreases. Then, just before it freezes, its density starts to go down, so that pure water's maximum density is at 4 degrees C. As it continues to cool, its density actually starts going down. When it reaches 0 degrees and freezes, its density drops dramatically, so that its solid form is much less dense than its liquid form. This happens because As liquid water cools towards freezing, it becomes more dense until the tendency for individual molecules to orient themselves in ways to allow the formation of hydrogen bonds makes it energetically unfavorable for the molecule to get any closer together. So below 4 degrees C, the attraction between the partially charged dipoles push the molecules further apart until at 0 degrees, the molecules get locked into a solid crystalline structure where they are uniformly spaced further apart than they were when they were moving relative to each other as a liquid. This is why ice floats. The fact that ice floats drives some major ocean circulation patterns and creates conditions in which heat can be trapped at depth in both freshwater and marine environments. If ice didn't float, the world as we know it today would not exist because oceans, lakes, and rivers would have filled with solid water from the bottom up long ago. And in the oceans in particular, sunken ice would never receive enough solar insulation to ever melt again. All of these important characteristics of water are due to its polar structure and the tendency for water molecules to form hydrogen bonds with other water molecules as well as with charged and polar compounds.